An AI can look at a photo of your dog and get every pixel right, and still confidently describe something that was never in the frame. I'm Kuro, and by the end of this, you'll know exactly why that happens. It's not the bug you're picturing. It's not looking, not the way you think, and the real trick took years to get right. Before real multimodal models, this got faked with a pipeline of separate tools. A caption model looked at the photo and wrote a plain English description of it. That description, just words, got handed off to a normal text-only language model. Seems harmless enough until you see what it actually throws away. Turns out, this pipeline had two real problems, not just one. A caption like a dog on a couch throws away almost everything else in the frame. And the language model never touches the actual pixels. It reasons about a summary once removed. So what happens the moment that summary is wrong? If a caption model already mislabels the dog's breed, what happens to every answer downstream of it? Take a guess. This exact failure mode has a name in the research. What if a picture never got translated into words at all? What if the model could read pixels the exact same way it reads words? As tokens. That's the real shift behind modern multimodal AI, and it starts with something almost absurdly simple. Here's the real mechanism, starting with the image itself. The photo gets sliced into a grid of small square patches. 16 by 16 pixels is a common size. Every patch becomes its own separate chunk, but a grid of pixel numbers still isn't a word yet, not even close. Each patch gets flattened into a list of numbers, then run through a linear projection. That projection turns every patch into a vector, a vision token the exact same shape as a word embedding. This whole approach has a real name, the Vision Transformer (VT), and it's still the standard way images get read, but on its own, it has no idea what a dog looks like as a word. Turning pixels into vectors solves half the problem, matching them to words is the other half. OpenAI's CLIP model from 2021 trained an image encoder and a text encoder side by side. Both were pushed to land in the exact same shared numerical space, so a photo and its caption end up close together. But pushed is doing a lot of work in that sentence. The training method is called contrastive learning, and the idea is genuinely simple. Feed it hundreds of millions of real image caption pairs scraped from the internet. Correct pairs get pulled together in the shared space, wrong pairs get shoved apart, over and over, millions of times, until something in that space just clicks. If both an image and a sentence end up as vectors in the same space, what does that actually let a model do? Think past labeling photos, the real use is bigger than that. Once an image becomes vision tokens, something genuinely useful happens. They get placed right next to your text tokens in the exact same sequence, no separate lane. One transformer, one attention mechanism runs across both kinds of tokens at once, though not every model gets built that cleanly. Not every multimodal model builds this the same way, and the difference actually matters. Many take a frozen, already trained vision encoder and bolt it on with a small adapter layer. Newer models like Google's Gemini line train vision and text together from the very start, no bolting on after the fact. Kuro, on the other hand, honestly, I'm the bolted on kind of multimodal. My drawing skills got adapted onto my personality afterward, and it shows. Native training would have been nice, nobody asked me. This isn't a hypothetical diagram. LLaVA is a real, open source model built exactly this way. A CLI blip style vision encoder, a tiny bridge network, then a normal language model on top. The exact same core idea, scaled way up, is what runs inside GPT-4o successors, Gemini, and Claude's vision models today, sitting right next to your text tokens like they're the same thing. Are they though? If vision tokens and text tokens sit in the exact same sequence, can the model tell which is which at all? genuinely worth a guess before we move on. This is the exact confusion worth clearing up before you call something multimodal. AI. OCR plus a captioner plus a text model viewed together is not the same thing. Each tool still reasons alone. True multimodal means one model, one shared embedding space, reasoning across every input type together, which sounds perfect until you see where it still gets things wrong. Remember that confident misread from the start of this video? Here's exactly where it happens, because seeing pixels isn't the same as understanding them reliably. Vision hallucination is a real, documented failure mode. Models confidently describe objects that aren't in the image at all. It says this with the same fluent confidence it uses when it's actually right, and honestly, that's not even the strangest way this breaks. Here's the stranger one. Spatial reasoning lags so far behind language ability that it barely looks related. Counting objects in a cluttered photo or judging exact left-right position breaks down fast. It's genuinely surprising these models write working code yet miscount 6 apples in a bowl. Why would one skill be so far ahead of the other? If language ability and spatial ability come from the same training process, why would one lag so far behind the other? There's a real debated theory here. What's your guess? That spatial mystery doesn't have a clean answer yet. But here's a second problem, and it's simply about cost. A single photo, once patchified and tiled, can turn into hundreds of tokens, sometimes more than a full paragraph of text. Feed in a high-res photo with every question, and your context window fills up fast. And that's before you even add audio or video into the mix. Multimodal isn't only about images. The same trick extends to sound and motion too. Audio gets converted into a spectrogram, a visual picture of frequencies over time, then patchified exactly like an image. Video is just sampled frames run through that same vision encoder one after another, same trick stacked in time, which almost makes it sound like the model is actually watching, doesn't it? One myth Kuro wants to squash before wrapping up. Multimodal AI literally sees and hears like we do. It doesn't, not in any perceptual sense. Every sense just becomes numbers in the same shared space. No eyes, no ears, just very well aligned vectors. So, what's actually stopping you from adding a few more senses to that space? If every sense just collapses into the same kind of vector, is there really a limit to how many modalities you could add? Smell? Touch? Where would you draw the line? Argue it out below. Let's fold this whole episode back together. The problem, gluing a captioner to a text model throws away detail and blocks real joint reasoning. The mechanism, patchify the image, align it to text with contrastive learning, feed both into one shared transformer. The trade-off, real understanding against hallucination, weak spatial reasoning, and a real token cost. That's how AI actually sees, not eyes. Just pixels turned into the same kind of token as your words. Next time, another piece of the machine running under your favorite AI tool. Did a multimodal model ever confidently hallucinate something in your photo? Tell Kuro below and subscribe.